So when we start Chapter 2 here, which is all on derivatives, we are going to, in Section 2.1, which we'll do slowly again over the next 3 days, really review the long-winded definition of what the derivative is, and the concept behind it. And then once we move past 2.1, we'll get into all those shortcuts that will make, number one, finding the derivative much quicker on some of these basic functions, but also give us the ability to find the derivative on functions that this limit process would not work for, simply because the math behind it would be too difficult. So we've got a whole bunch of shortcuts beyond that we will learn throughout this chapter. So just to review, the derivative of a function with respect to x is given by the limit as h approaches 0 for f of x plus h minus f of x all over h. So we're really looking for what the slope of the secant line is approaching as that secant line becomes more and more in line with the tangent line. So this first example, find the slope of the tangent line of the given function at the given point. So at 1, 5. So we're going to search for h prime of 1. Okay. First, we'll find the derivative formula. So h prime of t equals the limit as h approaches 0. That's a different h than the name of the function. But f of x plus h, or t plus h in this case, there's f of t plus h minus f of t all over h. So we'll clean this up. T squared plus 2th plus h squared plus 4t plus 4h minus t squared minus 4t all over h. So your t squareds are going to cancel, your 4t's are going to cancel, and every term left has an h. 2th, h squared, and h. So we'll lose an h from all of those. So you'll have 2t plus h plus 4. And then when h approaches 0, that'll just give us 2t plus 4. So there's our derivative equation. And then to evaluate that at 1, 2 times 1 is 2 plus 4 is 6. So there's our slope at 1. And then write the equation of the tangent line. So essentially we have a slope of 6 and a point of 1, 5. So we're writing the equation y minus 5 equals 6, x minus 1. So from there we're pretty much done, and we would just type in the equation of the line on our calculator with the original function and confirm that it's a tangent line. Okay, so I've gone ahead and done that, and there's our parabola, and then there's the equation of the line that we just wrote. Okay, another derivative, a more difficult type of function. Here's your f of x plus h minus f of x all over h. And this one takes some removing of the complex fraction. So of your denominators, your least common denominator would be this. So you would distribute, and you'd get 4 root x minus 4 root x plus h all over h, and then root x plus h root x. Nothing really cancels there, so now we might want to rationalize by multiplying by the conjugate. And actually, before I do that, I'm going to factor out a 4. So I would make this 4 and then root x minus root x plus h. That way when I conjugate, I can kind of leave that 4 out of it. Limit h approaches 0. Got your 4, and then when we conjugate, we get x. Outer and inner are going to cancel. Minus x plus h all over h. We've got a root x plus h. We've got a root x, and then we've got the binomial. So now your x minus x cancels, and then you just have negative h, which is going to, so it's 4 times negative h. So that's going to cancel with this one. So it'll just be negative 4 up top. And we get root x plus h, root x, parentheses, root x plus h. With the limit as h approaches 0, and we are ready to plug in a 0. So our derivative is negative 4 over, and if h is 0, root x times root x will be x, and this second binomial will be root x plus root x, which is 2 root x. So negative 4 over 2x root x, and then your 4 and your 2 can reduce, and I get negative 2 over x root 2 as my derivative. So it's not a terrible looking function by any means, but the work involved there, and that is what's going to happen as we look at different functions, is that this limit process is going to be, unbearable, and so we'll have our quicker methods. Really quickly, not an example at the bottom, but all the different notations for how to denote a derivative. So if your function is f of x, f prime of x works. This d over dx, so this is the derivative of f of x, and this is with respect to x. Obviously, that's the variable within the function. So like this one could be d dt of h of t. So that would be the derivative of h of t with respect to t, because that's the variable inside. So that's that one. dy dx, okay, if your function is y, that's kind of the same as this one. You're just using the f of x here. Here you're using the y. But the derivative of the y equation, the y function with respect to x, y prime, which we've seen. This one doesn't come up as often, but it's the derivative of the y function with respect to x as well. So 1, 2, 3, 4, 5 different ways of denoting the derivative. This next one at the top just gives us a regular quadratic function and a random line. Find an equation of the line, or there is a line that is tangent to this graph, but also parallel to this one. So we want to figure out what the slope is of this one. If we solve this for y, we're going to get negative 4x minus 3. So this has a slope of negative 4. So we want our line to be tangent to this graph, but with this slope. So we're essentially going to take this derivative and set it equal to negative 4, because we want to find the location on here that has a slope of negative 4. So if you do your derivative process, and rather than doing the whole limit as h approaches 0 out, I'm just going to cut to the chase and use that shortcut that we'll soon find out. But your derivative is 4x. We want to find the x location where our slope is negative 4. So when we do that, we find out that it's at an x coordinate of negative 1. So we've got to find the appropriate, we got to write an equation of this tangent line. So if we know the x coordinate is negative 1, we have to find the y coordinate that goes along with that. So negative 1 squared is 1 times 2 is 2. So our point is negative 1, 2, and our slope is negative 4. And then we will be writing the equation of the line that is tangent to this function. We found the point of tangency, essentially, where the slope had to be the same as this one, negative 4. We really had to we knew the slope first. We had to backtrack and find the point on the graph that had that slope. So writing the equation of that line, y minus 2 equals negative 4x plus 1. Okay, this next exercise is a little bit of a different skill. We have a graph, and we're going to sketch the graph of f prime, which is the derivative. So I would ask you questions like, what is the slope between 0 and 4? This is a negative 1 slope. Down 1 over 1, down 1 over 1, down 1 over 1, down 1 over. This is a negative 1 slope. So here's negative 1. So from 0 all the way to 4, there's a -1 slope. Now I'm putting open circles at both ends because we know the slope does not exist at an end point and the slope does not exist at a corner point. But the entire time here the slope is -1, so I'm just putting a flat line at -1. Then after that, the slope is +1. So from 4 to 8, the slope is +1. Again, open circle right at 4 and an open circle right at 8, but a slope of +1 during that stretch. And that's the slope of the derivative. Okay, this one's a little bit trickier. We know we have no slope at -2 and +2. Right at 2, our slope is 0. Prior to 2, that's a positive slope. This is very positive, right? Almost coming to a vertical. It's very positive, and then it becomes less and less positive until it's 0. So positive would mean above the x-axis. And again, very steep at first, so maybe like a slope of 10 at first, right here at -2, or just after -2. And still a positive slope, but not as positive, so decreasing. Okay, so it's positive, really positive, so we're up at 10, but then by the time we get to -1, it's still a positive slope, but not as positive. So the severity of the positive slope is coming down. And then we become a very slight negative slope at first right here, and then we're very negative by the time we get to 2. So maybe by the time we get to 2 or right before that, we'd be at -10 again. And what we get here is something like this. And actually, because this is becoming infinitely positive, as it's almost going to be a vertical line, looks like the top half of a circle, it's getting infinitely positive as you get closer and closer to -2, and I shouldn't say infinitely positive, infinitely large, here in the positive direction, here in the negative direction. And so the derivative, if this is g of x, this would be g prime. Kind of shows your slope. But we look for critical points, like where we know for 100% the slope here is 0, so that gives us a point. The slope all over here is negative, so we're in the negatives. We're underneath the x-axis. The slope over here is positive, so we're in the positives. So those can be tricky, and we'll do more of those over time. We'll actually spend a whole day on that eventually, but it gets introduced in this section. And then the last question tells us the tangent line to the graph of y equals h of x at the point -1, 4. Okay, so there's a point of tangency, and the tangent line passes through that and passes through 1, 2, 3, 1, 2, 3, 4, 5, 6. So this is the tangent line to some curve. We obviously don't see the curve. But there's some curve, and I'll just do anything random. Pretend it looks like that. That you could do any curve you want, but this is, I'm trying to give a visual that this is the tangent line to some curve. So we'll call this h of x. They want to know the slope, or the function value at -1. Well, that's easy. H of -1 is 4. The slope at -1, right there, it's going to be whatever the slope of this tangent line is. So that's going to be m equals 6 minus 4 over 3 minus -1, 2/4, 1/2. So the slope at -1 equals 1/2. Not an overly difficult skill, but the way that they present it is a little bit tricky, and to that I would say always try to sketch a graph on that.
Okay.